The final variation that we will look at is polymer solution. Okay, and again there are a lot of different processes. The first one is you add the polymer solution to the powder itself and sort of it's semi-dry, and then you press it. Because you have a lot of binder, it's going to deform at lower pressures, and that's how you make a lot of plates and things like that, and for dinner plates and things like that. And from there we'll go to some other variations, including some three-dimensional printing, which is a variation of selective laser sintering or the fused deposition modeling, in the sense that you can create three-dimensional shapes. And inkjet printing is another variation. Okay, we'll look at that. So semi-direct pressing, you have powders, you have a polymer solution which is partially, right, you add only a little bit of it, so you make like a dough, right, like a pizza dough, and you press it between two plates, and you can create some shallow parts like that. Okay, or you can even make cups and things like that in that manner. Okay, and then you take it out of the part. If the mold is porous, then it can suck out some of the water, and you can make it even harder by the time it pulls out of the part. So that would be one way to deal with semi-dry pressing. So you reduce the overall compaction force required for creating a shape. And by pulling out some of the, if it's water or a solvent, that can be removed through a porous die wall, right? You will be able to make the material have a higher yield strength. Lower the amount of binder, the higher the yield strength, and so you will be able to have a part that's removed and then it can be sintered completely separately. Alternatively, you can have a lot of solvent in the system so that you have a very low viscosity, so that you can pour it under atmospheric pressure as opposed to filling a mold cavity under high pressure like you do in the injection molding or die pressing, right? So you increase the amount of binder, the amount of pressure required to create a shape has gone down. So the suspension in this case is called a slip. Okay. So you, instead of having, say, something like 60 volume% of powder in the mixture, as in the case of injection molding, you might have something closer to about, I would say, about 30 volume% or something like that. Okay, maybe 40 volume%. So you have lower the volume fraction of powder, lower the viscosity, and more easily it can fill into the mold cavity. In this case, again, the same principle. It's a plaster mold. The plaster mold is porous. So you pour some material into the mold, you push it around for some time. As water comes out of the porous mold, there is a layer that is formed that is solid, and you can pour out the excess material back into that pot to fill in a new mold, right? And you can create hollow shapes in this manner. So that is called slip cast. And then after that, after it's dried completely, you can go ahead and fire the material, right? So you add different kinds of binders and powders, and you create this mixture, okay, called a slip. You pour the slip, you drain the slip, you remove the part. If you spill things around, you have to go ahead and remove some of the parts by machining. And you can then densify the part and then finally machine it. This is what the material looks like, and you can see it's, depending upon what it pours and how fast it pours, there can be like a very messy operation. Right? Powder is dust. So most powder processing techniques can be very messy, right, depending upon the process stage. And so that's something, so as the complexity of the process changes, being able to confine the mess becomes more and more important. And so if you, instead of having something like this, if you have pellets, then the operating room is a lot cleaner. And so, and because the melt is all confined within the machine, right? And so the liquid's not all over the place, like you're sitting and painting a room or something like that, right? It's confined, and so those are some advantages you can see of going one way compared to the other. But it's lower pressure, it's lower viscosity, it's aqueous processing, so it's less expensive for some volumes, and because you're just building a plaster mold, you can make very large parts very inexpensively, right? You don't need a massive metal mold to make large parts. And with slip casting, you can make parts that are about as high as this building. And electrical insulators in power transmission are typically made in that manner. You can also make something very small, right? Something like that can be typical with slip casting. So the key thing, yes, go ahead. Correct. Water. Well, all the toilet bowls are made this way, as one water container. Correct. I mean, well, I mean, depends upon the tank. Are there ceramic tanks on the top? They're plastic. Okay, plastics. No, then that's typically made by reinforced plastics or they're molded plastics, and so that's different. But these are primarily used for ceramics. So anything that you can see that is porcelain, that will be made by something like that. If you go, I mean, I don't know whether where you were living there was a power outage, but near most electrical substations, you will see these large insulators, and typically they are made by. In terms of understanding the process, the main thing is how to control the wall thickness. Okay, it changes as a function of time. The longer you wait, the thicker the wall that will be built. It depends on pulling a pressure drop through the porous mold. You can create a vacuum and you can pull out more water. Okay, it depends upon the viscosity. The lower viscosity material, right, will flow more easily out and in, and so you can build a higher thickness, right? So these are some kinds of variables that you can think of. And again, this is again an example of what I talked about in terms. If you take L as a geometry parameter, how thick a wall am I building? If you take viscosity as a material property, depending upon the powder to water ratio, right, this viscosity is going to change. So that's a material. This is a part geometry. Time and pressure are process variables. Okay. J is basically the volume of the casting divided by the volume of the liquid removed. So if you think of phi as a solids loading or the volume fraction of powder, 1 minus phi is the liquid, and J would be 1 divided by 1 minus phi. So it's related to the porosity term. Okay. Higher the porosity, initially, the more quickly you can remove the liquid, and so the faster the wall thickness you can build. Yes. Higher the temperature, lower the viscosity, right? And higher the wall. Very good, right? So now you begin to see that geometry, process, material can be interrelated. Right? Simple equation, but gives you an idea of how to design, how thick a part I want to make by slip casting. What variables do I have in control? Right? How much vacuum do I pull? How long do I wait? How high do I heat the mixture? Right? All these can be related to that. K is the permeability of the mold. So depending upon the porosity of the mold, you will be able to pull more and more material out. And so that's roughly what this is, a wall thickness plotted experimentally as a function of time. The longer you wait, the thicker the part, right? And then there are a bunch of different parameters in addition to that. Pressure, if it increases, thickness increases. W is the weight of the liquid the liquid that is being removed. T is the temperature parameter. You can see as you increase the temperature over here, thickness goes up. Okay, so it gives you an idea. So main thing is, as we go through all these different processes, you have to look into process design as an important attribute. That's what we're trying to impress. Became a little bit long, but tape casting, again, the story is similar. You have a solution of a polymer, right? You put some particles together. Earlier, we saw a way to create sheets by using a melt additive. Do you remember which it was? There was a process we saw about creating sheets. Yes, so the roll forming, right? So now this is a way to make thin sheets using a polymer solution, right? So you have a suspension of particles in a polymer, and you have a blade that controls the opening of the tank onto a film that is being rolled out in a drum like this. So there's one drum that's moving, there's a sheet of plastic that is holding the layer that is coated onto that. The coating thickness is controlled by the gap between the film and that, right? And so you can spread a uniform sheet. The sheet is dried out and rolled over, and then after that you can stack different sheets together. This is what a machine looks like. You have a roller over here that is feeding the sheet in. There's a coating happening. Over here, you can either raise the temperature or you can have airflow, and you can dry out the solvent or the water, and you can create a dry sheet that has more strength. It's like making paper at that point, right? So thickness depends upon the gap over there, the speed of this belt, right? It can depend upon the drying temperature. It can depend upon how much powder you have initially. The more powder you have, the lesser it will shrink, right? And so the final thickness will depend upon that. Okay. One way it's used for is it's used for making a lot of integrated packaging, where alumina is a dielectric. You print conducting wires and you stack the sheets one over the other, and you interconnect the layers, and you can create different. This is an optoelectronic package that is made in that manner, and it could have as many as 60 or 70 layers, right, that are interconnected by conduct. So you have a sheet, you cut it out, you punch holes through that, you print out um, electrical conducting lines through pastes, okay, and you put all of them together to form the design that the electrical engineer wants for the overall device. Then you take that whole thing like a cake and you put it into a furnace, you burn out the polymer, you fire the particles together and a sintering, and you get a dense object that you can move around, right? Depending upon the sintering temperature, it can be a high temperature ceramic, co-fired ceramic, or it can be a low temperature ceramic, okay? So mainly, if you see, those are the gold lines that are printed out on the top layer, okay? And you can have layers in the intermediate zones as well. And so you take those sheets and you begin that are ceramic, and you print these kinds of metal layers and you stack them through. You punch holes through the layers and you fill them with metal as well. The holes are called vias. The main thing is, if you look at a circuit drawing, right? Suppose you started out in 9th grade. You show an electric circuit with resistors, capacitors, right? You apply a voltage source and it's this big and in one dimension, right? Assume now that you can connect all these layers on multiple sheets and you can space them out to very small regions. And you can, because you put, imagine the difference between reading one book that is fully spread out on a wall and holding a book in your pocket, right? That's what is miniaturization, by stacking multiple layers together. That is possible by creating these kinds of sheets. Okay. The temperature, so high temperature, depends upon the amount of glass that is there in the alumina. Glass melts at a lower temperature. These are some kinds of polymer additives that are present, right? The metallization, because it can be fired at a higher temperature, tungsten and molybdenum can withstand high temperatures, okay? And they can also dissipate heat much more readily. So typically you sinter around 1450 degrees centigrade. If you increase the amount of glass, okay, fine, thanks. You can fuse this material. You can sinter it at much lower temperature compared to that. Okay. Of course, if you add glass, you change the dielectric properties. In some cases, the insulation that you require is lower compared to in other kinds of circuits. And so typically you can make less expensive material, less expensive components this way compared to over here. Mainly if you have more density of circuits, they need to be electrically isolated from each other more efficiently. And so you need a better dielectric constant, more alumina compared to glass. If the density of circuitry is not that much, then you can get away with something like that. Okay. But basically it gives an example of some kinds of binder additives, some kind of powders, and what type of end component you can make. So it's a very simple shape, a sheet, but the final component you can make can be highly complex and very high volume. I'll quickly go through a couple of examples and we'll take a short break. But mainly, just like with selective laser sintering, you scan the laser beam, right? And then in the case of fuse deposition modeling, you moved around an extruder. You can now move around an inkjet, which is now, instead of an ink, it's a polymer solution. It's a binder solution. Okay, so you make the powder bed, you put droplets of binder around like ink droplets, you hold you bind the particles together. Where the inkjet printer moves, right, you'll have bonded particles in the layer. Then you drop the drum, you add another layer of powder, you put another inkjet of polymer solution, you bind particles. Unbound particles can fall apart, and you pull out a fully three-dimensional component, right? So you take a CAD geometry, binders deposited in certain areas, binder holds the powders, unbounded powders remain loose, and you can pull out the part. You can take out the part and you sinter it, right? So this is the example. You have a table that goes up and down. You have an inkjet printer that can go in the XY direction. The drum can go in the Z direction. You put a layer of powder. You can keep building a part, and it can be a hollow part like that, right? You can control the speed of the inkjet. You can have multiple jets moving around as well, and so that could increase the speed at which you could remove the part. You can make the part, right? But the idea is same. You have a computer file with a geometry, you slice it into layers, and whether it's the laser beam, whether it's the extruder head, or whether it's the inkjet printer head with the binder, you can use pile of powder and make a three-dimensional component one at a time, right? Alternatively, just like ink is a suspension of particles, very fine particles, in a solvent and maybe a binder, right? When you're beginning to deal with nanoparticles, now you're dealing with a particle size that is small enough that it can remain in suspension readily because gravitational forces won't allow for settling of particles as much. Also, it is small enough to go through a very small nozzle size of an inkjet, right? So now you can create metal inks. And one thing that people have been doing is trying to take gold nanoparticles. Okay, a lot of people are synthesizing gold particles, formulate an ink, and now you can begin to print that across to make conducting circuitry. Right? Normally, what people did for making different wires, you could have a paste of silver or gold particles and or copper particles, and you can create relatively thick wires. The idea of being able to use an inkjet droplet is you can make submicron or tens of microns. You can control the droplet size very well, and you can make much thinner wires more rapidly. Another approach people have been using for making wires and printed circuit boards is they will plate an entire layer of copper, say, onto the surface, or they'll take a copper foil and they will stick it onto a fiberglass board. Then they will silk screen print a mask and etch away certain regions. and then leave behind a circuitry. That involves more process steps, and it also involves a lot of waste because etching solutions are typically very corrosive and toxic. Disposing those solutions is not easy. By inkjetting, you're using less material, you can make finer shapes, right? And you create less wastage. That's something you can do. In that manner, you can dip something in, like Raphael is doing, into a suspension of particles, and you can create coatings. Instead of a film, it can be a foam, right? You can apply an electric field to do the same. And if the particles, again, when you're dealing with nanoparticles, right, particles are small enough, and if they're charged, they can move on the applied electric field, it can move from one electrode to another and can create a coating. You can change the complexity of this shape such that internal features can be coated uniformly, catalysts can be coated over a wider range, things like that, right? So as you go to nano, so inkjet printing, electrophoretic deposition are all different kinds of solution processing that take advantage of small particle size and low concentration, right? Because synthesis methods typically will have a suspension that is created if you know how to create it with fine dispersion, right, without agglomerates. You don't want to dry out the powder and form agglomerates again and then redisperse them. You want to use it directly as a suspension, whether it's a Stauber synthesis or the, right? So now the idea of using suspensions, right, polymer solutions that are whole dispersing particles, right, becomes more and more important when you're trying to deal with creating shapes out of nanoparticles. Okay. So that's my summary. Sorry, this part of the class went a little bit longer, but now you have an idea that we looked at 3 categories of binders yesterday, and now we, based on that classification of polymer melt, polymer solution, and solid or no additive, you can create a wide variety of shapes. The second thing that I want you to leave away with, the shape you're making, the material you're making it out of, and the process you're working with, and the process conditions are all interrelated. So that is a message we'll build on in the next class. We'll take a short break now and maybe meet in about 5 or 10 minutes and try to take just one process, injection molding, and look at some examples of how do we understand quantitatively the relationship between geometry, process. What we learn from there can be designed and applied to in different ways to different process or materials or geometries. All of you are working with developing new materials in some ways, right? Or developing some new process. The idea is how to understand how to use that material or control that process to the point that as you scale up the volume, you can control that quality of the material and quality of the product that is made from that material, right, on a consistent basis. The penalty for that, if you don't do it, is you might have some reactors that are very efficient and some reactors that are not. Right? You might have some components that are very hard and some components that are not. Sheryl is going to have some solar energy conversion devices that are going to be super efficient and some that are going to fail. Right? There are going to be some porous structures that are going to be made by Raphael that are going to have low strength and some are going to have high strength. Your clay particles are going to be all over the place. Some of your medical implants are going to function normally, some of them are not, and then you're going to have a big lawsuit, right? So being able to understand how these things get to work together and building that over a period of time as a logic structure becomes very important, right? So that's how we will close out this portion after a short break. Okay, so see you then.